G'day guys. Just making sure they haven't got World War III going on out in the hallway. No, I think it's all good. Yeah. Anyway, that's how our board came up. Nice and clean. And just for the hell of it, for educational purposes only. So, as you can see, all the part numbers are ground off. But I want to have a little bit of a talk about these two chips here. The other day I said, I called this one here a coprocessor. I shouldn't have called it a coprocessor. It's actually a programmable logic array. And it had to be in this design because the processor they're using, the Hitachi thing or Renesas, where they call themselves now, it just doesn't have enough speed, headroom, and it can't do everything that was needed to switch all the functions on the board, and it was basically outboarded to programmable logic array here to control all the switching of the 4053s. Basically all your switch inputs here, they all loop back into the programmable logic device there, which I have got the number written down here somewhere. This is old hat, really old, it's no secret anymore. Yeah, XE2C384 CPLD, complex programmable logic device. There's a lot of that stuff out there, and it's because these things are, this is technically nowadays a slug. It just couldn't do enough sampling and control everything. Yeah, it's basically where it ended up. So yeah, it's, you know, it's a whole heap of switches, some op amps for amplification across the channels, logic, basically controls, supervisory circuits for the power supply, and some other switching down the bottom there, power supply driver, and the input channels there, all 4053s again. And when you actually get the paint off these boards and you look at it, right, and this is just my opinion, it's not very complicated. The most complicated part of the whole board is in the microprocessor and logic, and actually that's just dead simple. It's just timing waveforms mainly. So there's nothing rocket science about it. It's very, very straightforward. Now, 80% of this board, right, 80% of it can be, I got a new one in, hang on, see, I've got it fired up at the moment. There we go. Can be done on that. This, I'll unplug it. So it's got an LCD screen on it and everything, so it's quite handy. That's it there. It's got a little LCD. You can unplug it and put a bigger one in, or whatever you want to do. You can interface it many, many ways. The processor they used on those GPX things ran CPU speed 20 megahertz. Okay, so even though it sounds like a lot, oh, it's running at 20 megahertz. Well, actually, that one there is we can get that going at 550 megahertz. So, right, and that's probably about 70% of a detector just on that board there. But this one, the new one I've got in, I just got this one. I've got some more coming, by the way, different ones. But this one here, that thing absolutely hammers and flies, and it's got some onboard memory on the back there. It's got some couple of chips. It's also got internal memory. There's a different version of these STM32s, and some of the later chips need outboard memory. They just don't have much. They only have 256K of memory or something, very small amount, where that one there has 2 megs of memory on board. So you look at a lot of the designs done with, say, the STM H750, and they've all got WinBond memory chips around it. So it just takes up board space. If you can do everything in 2 megs, you can just do it on chip. And yeah, however you want to do it. It's very good. I'll tell you, give some basic things on the new boards compared to the onto the things used in this. This thing here, right? It's got basic 16-bit timers. The new board's got multiple 32-bit timers. The timer resolution on those old chips is limited, and on the new boards, these boards here, we get the timers. See, this is important. Timer resolution for all your transmit, receive, turn on, turn off times, sampling times. You can't have it doing this, right? And it's going to be dead accurate, and it's going to be dead accurate on the next lot of pulses and all the way through. You can't have it all over the shop. And if you try to do it with one of these old chips, you just wouldn't have the resolution. You wouldn't have as much sampling points as what you would require to make a really good detector. You just wouldn't have the ADC depth, the resolution. There's a whole heap of things that were, having that thing there with all the helper around it trying to make it or help it do things, it would be very, very limited. GPIO speed, on this under 10 megahertz. On the new board, over 100 megahertz. So it's just amazing, right? Even on the old one, ADC control, all externally controlled. And on the new boards, integrated high-speed ADC and plus external control. DSP capability on the old one, none. FPU, SIMD on the new ones. So there's a lot of reasons why you can't build a very small detector on that technology platform, because just a lot of things you need on there to make it work properly. But even all this stuff here, like all these op amps and switches, all that can be massively miniaturized now, down very, very small indeed. And there's different ways of doing this. The most important part of probably is you keep your timings accurate and very high accuracy without any strange offsets in integration section of the detector. I've seen some that still use analog integrators, these things here. It's by look of it, if you look around there, there's a lot of capacitor networks, resistor networks, and that's all much the same around there. So it's probably a variation on the old way of doing it, using high quality polypropylene capacitors and stuff like that. But I'm not going to go into the nitty gritty of it all. Yeah. So it's very interesting. The resolution in the timers, 184 picosecond resolution. If you try to use one of those old 20 meg chips, it would be all over the shop. It wouldn't make a very good detector. So that's why they've had that programmable logic add-on, which just does a lot of the housekeeping stuff and control. Okay, where are we? So the high resolution timer, how's that? It's equivalent for 4.32 gigahertz. That's right there. Yep, it's very important for critical edge placement and timing functions, which you need. There's some more stuff here. You actually can do some DSP on that actual chip as well. Where are we? It's got heaps of IOs on that chip as well. It's really just absolute overkill. Um, and you can do everything on that chip. You don't have to outboard anything. Just be very careful how you do your actual main oscillator. Do an outboard oscillator. You can use the existing, well, you can use the existing ADC. It's got three 16-bit ADCs in the new chips. You can use those, but you're probably better off outboarding that into one of the chips that's got multiple, like an 8-channel ADC, and do lots of magic in something of that nature. Yeah, I've had a look at these things, and everything using the 4053 multiplexer switches in these things. There's all sorts of little artifacts that get generated with the switching. Proven that. Yeah, so it's it's amazing. So they've got 16-bit ADCs, 3 of them in there, but if you want to crank it flat out at the highest rate, it drops back to 12-bit, but the sample rate is 5 megasamples per second. That's pretty decent. But even so, if you're doing a lot of sampling and all the control in it, yeah, there's better ways of doing it. There is. I'm not going to say what they are, but there's a better way of doing it. Yeah, where are we here? Yes. We know that. That's exactly what I was putting in there before. Yeah, so it's very limited. The old design's very limited in their sampling. So if you get basically, if you get, say, let's multiply the sample times by 100 and look at the resolution you can get, especially really, noise averaging, the preciseness of ground balance on very weak signals as well. And with those designed, if you really want to go nuts, you can stick a 24-bit ADC on the thing as well. And there's only one thing that was missing, but it's easy to incorporate, that we can use differential ADCs. And yeah, I think most of it was nutted out to make a very, very small, powerful detector. Basically, all you want is some switches, like I've been talking about solid state switches with this front end, flyback management. And do you need, I'll tell you right now, do you need all that? Do you need all that? No, you don't. Because now we can buy 18-volt lithium batteries, or any voltage lithium batteries, or get battery packs made up for higher voltages. So it's easy enough to just use a higher powered, higher voltage battery, and you can then, if you want to do different pulse voltages, keep it all the one voltage and just alter the time. Get more, to put it all up at 15 volts if you want. I mean, you get more energy into the thing. Probably might have to redesign the coil. That depends. But there is, I mean, I'm not joking. Very soon, you're going to have detectors available, and they're going to be about that big. That will be what's in the control box. If you want to get the miniaturization and make it very efficient, we can utilize the new GANFETs. Basically, you don't need any heat sinking whatsoever with those things. They're just very, very, very low on resistance for you. Say you want to drive the coil. They're small and minimal heatsink. You just do it on the board. But the whole thing's just a bucket of. If you look at a metal detector, it's just basically a transmitter and receiver and a bucket of switches. That's a basic format of it. It's very, very simple. And, in my opinion, I'm going to say this in my opinion, and other people have agreed, and other people have said it around the place. The only reason, in a lot of cases, that IC numbers and things are ground off is because it's so damn simple. There's no other reason to do it. If it was complicated and it was tons and tons of programming and it was extremely tricky and everything, well, you just leave the numbers on because you'd think no one will ever work out the code. But if you start grinding numbers off, it's it's trying to disguise the obvious. It's very easy to work out what all those components are. It's just a matter of just while it's on, you go around and probe it. Over years, you just learn chips and you just go, oh yeah, that's that. I could probably, tell you what they all are off the top of my head. And I might leave one or two out, but yeah, it's mainly the secret in all this stuff now. It is locking the code and coming down to utilizing a lot of DSP and very advanced filtering. Anything done normal component level can be easy probed and worked out. Like David, as a joke, said the other day, he picked up a 6000 board and looked at me, and he said, "Oh," he he held it up and he goes, "Oh, that black module? It's all sealed up." And I go, "Yeah." He goes, "It's probably got your variable dampening or variable gain in it or something." No, it hasn't. But he was just basically saying something that was quite funny because if it has to be sealed up in resin, it must be very simple. Must be very simple, like my damping modules, because I fill them up with resin. But that is actually for a particular reason. And I suppose Minelab's doing it was for a particular reason as well. But as time goes on, and all this is, at the time these come out all painted in white paint and stuff, you'd look at it and you'd be going, what's in there? What's that? How does it even work? All so complicated, but just over time. I mean, if you sat down there for 3 months and actually worked on it full time, you'd have it completely nutted out. It's no big deal. But just over time, just little bits and pieces falling into your lap, and you'd say, it's very simple. It is not that difficult at all. It is not, as complex as everyone makes out. It's not at all. So that's what it is. Everything's simple, especially when you know how to do it, right? That's quite funny saying that, but yeah, it is simple. It's really simple. I never ever bothered looking into the digital side of it, and I just sat there the other night and I just said, look, I'm gonna show you a trick. I'm gonna show you a trick. Anyone working on one of these, right? And I'm going to say all this is for educational purposes. There is no back engineering or anything of that nature. You wouldn't do it like this anyway, okay? You go broke. Their parts that cost too much and it'll be a slug. But compared to new detectors, right? But the thing is, for educational users, I'll show you something that could come in very handy because, once you get the paint off, there you go. You can get onto every contact of these things. You get onto every contact. And the thing is, the way it's done, a lot of tracks go under components and they're through the board and they're here and there. They pop out little through plates on that side, go under, back up. And it's just a complete mess of, stuff. And the worst thing is, if you tried there with, say, a multimeter in beep range, so it goes beep on continuity, and you got onto one of these pins, say you went onto the first pin of that, 4053 there. And you went, oh, where does that go? And you sat there and you went, poke, poke, you'll be there forever. You will not be able to do it, right? It just, there's hundreds and hundreds of places that could go, and it might even end up under something and then go somewhere else. So I'm going to show you a trick to speed up finding out. This is, just say this is for repair work, okay? Education, repair work. And I'm going to have to grab a multimeter. Oh, I'm not going to go to the bench. Well, I could, but then, no, I'll do it here. I'll do it here. So I'll just get a multimeter and show you how this is done. Okay. Guys, any of you guys mucking around for any of this stuff, you're going to love this. Okay, got our multimeter. It goes beep when we put the leads together. So what I've got on here is 2 pointy leads, compliments of AliExpress. I don't know if you can hear that, but it is beeping. And what you do, you get on your board. How about I do this? I'll just angle the camera down to make it easier. Right, so we go down there, do it here like so, and I'll put that over there a bit. You can see the board. And say if I went on to this first leg of this 4053 here, which I'm probably not in the first leg, I'm upside down, but anyway, you get the idea. Now, if you wanted to work out where that went, you'd have to do this. Well, obviously, that's a common, but right, doesn't go to any other leg. Does it go to the other one next to it? No, 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 no. That side. Oh, there we go. It does go to the, it's probably common all the way through. Yeah, it's power supply rail. But there it is there. Hey, I'll get on one of the other ones. I'll get on an output or something. No. Yeah, there'll be an input or an output. I just don't know the pin numbers off the top of my head by looking at it. But you want to try and work out where it went. And you went all over the board like this. And you'd never find it. Unless you went up here, and you'll find it here somewhere probably. Or maybe not. No, go somewhere else. But anyway, what I did, that was exactly what I'm saying. Where does that pin go? You want to know where it goes. Now, with that collection of brushes I got, in the magic lot of brushes, the brass one, right? And what I did, this is I thought this was quite interesting. I get the multimeter lead and I stuck it in the brush, like so. I would get something a bit better than this and make sure they're all jammed up together, but stick your multimeter lead, not poking out like I had, but in the brush. So it's conductive. Not up here because the bristles aren't touching, but what I'm saying is you've got to probably squash them a bit more together, and it would probably beep anyway if I did that. Yeah. So something with a lot of bristles on it, conductive. But if I get this, and I'll do it sideways, so I get in the end part of the brush, this is very difficult because the handle's bent and yeah, you need 3 hands to do it. But if you had it like, God, okay, I'll try and hold it like that. If you had it like so, it's all conductive around there. Right, so what you do as a quick way to track out a board, and I would have something a bit better than what I've got here. This is totally bodgy, but you know, you can get round brass Dremel brushes and just tie your, you know, I probably got some. I'm not joking, I probably have. If they're in here. I've got a whole heap of diamond ones, but I do have brass ones somewhere. Okay, I've moved them. But the idea is, if you can get that in your bristles, your brass bristles, your brass bristles, this is so If that handle was straight, it'd be really easy to do, but because it bent down here, it's really hard. So I have to jam a finger under there or something like that to do it. But anyway, if I went on this thing here and I said, oh, you know, where on earth, oh, you can hear it beep. Well, I've narrowed it down. It goes down to one of the legs on this. Oh, it also goes there. There. Obviously, I'm on a power supply. Hang on. I'll get on one of these. Hang on. I'm just trying to work out the, 1, 2, 3. That one there. That should be right. Okay. Now we'll go here. Anyway, where that leg goes, when I hit it, it will beep. But I've probably got this set up wrong and I'm all over the... Anyway, you get the gist of it, what I'm trying to say. With the brass bristles, if you can make them all conductive, just bloody thread a bit of thin wire through it all there and have the wire come off and go to your multimeter lead. Make it easy for yourself, unlike what I was trying to do, because it makes it making it hard. But if you went around a circuit board and you're on a pin and you're just going like that, eventually it'll beep, or may beep in double, or you maybe even want to solder a small wire to it, which is a pain in the proverbial. Flip it over, have it on a lead, and then go over this side. And actually, by doing that, you could eventually map out the whole board. It's time consuming, but if you want to do all that one by one to one area on the board, you'll be there forever. I know someone's done it on a couple of detectors, and all I say is that they had a lot of patience to do that. But you know, if you want to get onto this and you say, oh look, you know, we want to find out where something goes, you know, it's not going to go to all the active parts. If the resistors in the way, there's capacitors in the way, there's all sorts of stuff. But say you just want to look at the off the front mylar where the switches are, like these things here, and you say, oh, which one does it go to? Well, you know it goes there. It goes to those little inductors on the front there. So that one, there we go. We know it goes there. And we say, well, it's going to come down here somewhere. And you'll say, but wouldn't that go to the 4053s direct? No, it goes through this PLCD chip. If I go along here, there we go. There, that pin. So that's beeping away on that pin. So what it's doing, it's coming off the switches here, going off to this, and then it comes back onto these. So basically just having a switch control electronic switch, it's going into this, and it's probably, you know, got some, you know, on off type switch set up in it. It could have more. It's programmable. You can program it so one input can control, you know, 5 outputs or something of that nature. But if you actually went round and looked at it, I'm just saying this hypothetically and just my opinion, if you actually worked out where all the connections are, you could probably work out exactly what's going on, and you could probably recode that yourself and make it do exactly the same as what it was designed to do without ever looking at the code. So that's how it works. This thing here, you know, all that's doing is generating a lot of timing and so forth. You can have a look at it here and you can poke in those test points there. The other thing too, when you get all the paint off the thing, which makes it great for serviceability, if you want to repair your own property which you've purchased, you can do what you want with it. But there's test points on each one of these channels here, and on the other side of the board, there's your integrators there. You got 3 test points here, 1, 2, and 3, and you got test points for your regulated power supplies there, and there. there's other test points around here. Until I got the paint off, I didn't even know these test points existed, but they are there. They're various test points for things. So that is that. You can actually, just for serviceability, track the whole thing out and work out how it all goes together. Not that you need to. It's very, I'll put this back up, but it's very, very old hat now. It's good, it works, it's functional, does everything it's meant to do. But now it just doesn't have to be that big, right? So it's quite small. I'll just see if I can get in here on this. I'll plug this little dev board in. And I don't know, I've got to get it around that way, you won't be able to see it. I don't know if you can see it there. But this little board, they're actually, or this particular one, you can put a camera on it. And I don't know if you can see the display. If I push that button there, it's got a little bit of a self-test routine in it. And it'll come up and it's going to say, camera test, camera not found. Okay, so with these things, there's provision there. You can put a little miniature camera on it, and you can interface it into, you can. I think this one's got an SD card reader on it too, has it? It's an SD card reader. Depends. They've got a lot of input-output things on it. I think so. Maybe that is a miniature SD card reader. So you can actually build one of these up with metal detector and add storage on it for whatever you want. Maybe just interface it and click a button, run it with GPS and just say favorite find or something, or hook a camera to it and photograph where you dug your nugget. Something. Yeah, all sorts of weird stuff you don't really need. All the bells and whistles, we call it. But yeah, that's quite nice and small. It's even got one of those things that are on the LCD control board for these things, and things you bend over and they break. I think a few of the detectors have those, even the newer ones. But yeah, just remember that way, oh, they'll break. So yeah, I think these boards here, this is the leaded version anyway. If you can see it, it's got leads on it. They got the ball grid array type devices as well with all the connections underneath. But if you blow one of these chips up, you can unsolder it and spend probably $10 and put a new one in there. If you've got one of those ball grid type arrays where all the connections underneath, you can, but it's very difficult to replace the chip. You've got to get it damn hot. It'll probably damage the board. You kiss your LCD goodbye. All liquid expand and that'd be the end of that. And it'd just be difficult to try, and it's so fiddly. I've done it before, but it's so fiddly. It's super fiddly. And and you get one damn pad that doesn't connect after you've done all the rest of them. There's 100 pins or so, 120 pins or whatever these things have in that version, and you'd be screwed. You'd be going backwards. Even with this earlier one here, I'm trying to remember what that was. It's an STM32 something or other. I can't remember off the top of my head which one it is. But like I said, the other one, you got straight provision to put in an OLED display. It's basically all there, either or. And yeah, it's interesting, isn't it? How technology moves. If you get something like that and you just go, oh, okay. Basically, that's your size difference. Even if you make this as long as the rest of the board up here, right? That's how big it would be. That you'd fill heaps of stuff in there, and you get rid of all this stuff. You probably don't need it. The only thing I would suggest that maybe you need is a decent electrolytic capacitor on the power supply for the transmitter. That is probably about it. The rest of it can be done with sufficient isolation using various techniques to keep the noise out and ripple out, and dual or triple ground plane type stuff, separate ground planes for your analog and digital, and just get the noise out the whole system. So yeah, I actually ran the code up for a complete detector on the earlier version, and run it through a sim, and it actually works quite well. It all good. Thanks to Mr. ST for making all sorts of lovely software available, and making some very nice chips and development boards available as well. So maybe, I was just saying to David too, I was saying to David the other day, I said, what should we do with this? Shall we actually base a whole detector on a dev board, which anyone can go and buy, right? Go and buy one of those. And so you got all the pinholes there. Can you see those? That's you can use those for your connections. And what you do is you build a baseboard up with all your other stuff on it, and just go bang, and hit it with your soldering iron all the way along, solder it in, away you go. You have a metal detector. Not hard, and to make something really, really good. With some of this stuff too, actually there's some newer generation stuff coming, which yeah, it's coming. I'll just say that, some newer generation stuff coming. There's all sorts of things happening all over the place, but like every project I look at where people have started and they don't finish it really quickly, it becomes old. So it's superseded so quick. But how far do you want to push it? Like it's like if you want to go and drive from one town to the other. If you take an old Volkswagen or take a damn Maserati, you're still going to get there. One's probably going to be a little bit quicker than the other, but is it speed you want? Certainly there is speed aspects into the amount of samples and stuff you can take, and just the communications through your boards and through all the semiconductors. You want it to be fast. You don't want time lag in there. You go all horrible, but it gets to a point where it's, if you go past that level of physics, it doesn't make any damn difference. It's like I don't know. It's like coming up with a better bucket to carry a bucket of water, if you know what I mean. I mean, a bucket is going to do it. You know what I mean? Keep it simple, but have it effective. So, yeah, there's a few guys out there playing with this stuff I know of, which is good. A lot of them are overseas, actually, where they find it very difficult to get metal detectors. And you probably see some of the comments on the channel about that. And yeah, but yeah, this sort of stuff here, relatively cheap, or I think that one wasn't that cheap. The other one was about, I don't know, I got two of them. So yeah, it could have been $20 or two, sort of thing. And this one here, this is a bit better. Could have been $24 or something. In the scheme of things, it's if compared to a $10,000 metal detector, it's not much, is it? So if we look at all the stuff that is now available, and especially with AI, that'll code with you and pick you up on a lot of balls ups. It makes it very simple. You got to just give it the right instructions. So it does help to have a grounding in what you're trying to do. You just can't magic it. It won't happen like that. But you know what you're trying to achieve, and you can actually get there. And yeah, just cross-reference back all the time and just ask questions in a different way. Sometimes you might get a different answer. So you've got to be very concise. You've got to have all the information in there. They've fixed up this one I'm using at the moment. They've allowed it to access its own memory from all the chats you've had. And if you said something and you've gone off on a different tangent to something else that was in there, it'll actually pull you up on it and say, oh, you said you're going to use this. And now you're saying you're going to use that. And then you got to correct it. And it goes in and fixes it up and keeps on going. So, yeah, it's just like having a very smart apprentice, I suppose, who's looking over your shoulder. It's really good in that way. So, yeah, it's quite funny, some of the stuff it comes up with. It's a bit cheeky too sometimes. But yeah, if I go through the 80s, should I go through here on the ADCs? It's interesting. It was trying to push me into using the Delta Sigma type ADCs for a particular reason, and I know why. It's a noise benefit, but I want to stick with SAR ADCs, and there's a reason for it. And after explaining my reasoning to it, it sort of got the gist of it and ended up agreeing, but then came up with a whole heap of enhancements for ADC, SAR type ADC, sorry. And yeah, so anyway, if I let you look at this, it'll give everyone thousands of ideas, but yeah, it's good. It's done everything on a cost analysis basis as well. Like we're talking about ADCs and the way it's going to do it, and it's basically said, I like this. It's going to cost $24 extra to do it the way I wanted to do it, and it came up with the 24 extra cost is trivial compared to, yeah. Oh, I'm not going to read all that. That's just too much. But there's a lot of important factors to look at when doing this stuff. It's you got to how do I put it? It's like if you wrote an essay. If you started off and wrote everything neat, it usually stayed pretty neat throughout the whole thing. And if you were rough and you were quickly writing it, it would be rough through the whole thing. Sort of a bit like that. You got to be really concise and accurate. And if you do that in your initial stages in the design work, or co-designing, should we call it? We'll call it a co-pilot. That's basically what it is. And it just knows that if you do anything stupid, or you go off, or you've forgotten something, it'll just say, hey, you haven't allowed for. And the funniest thing it actually did at the end of it all, this one, which, hang on, yeah, it's gone into great detail, why, how, and all the rest of it, and why things are fast enough, why things need to be improved, yeah, everything. So, and at the end of the day, I did this. Where are we? There's pages and pages of this, pages of it. I was making suggestions. It was making suggestions, and it picked up on something really funny. I don't know if I should mention it, but it was with another detector that's out there, and I was basically just having a bit of a discussion of what they used, and it said, why did they use the da-da-da when you could have used da-da-da and you wouldn't be keeping Winbond in business buying memory chips? We'll leave it there. But it's quite funny, actually. Dear. Because there was no benefit in using something more expensive than something cheaper. The cheaper one had something the other one didn't. It was more expensive. But anyway, There's reasons. Went over the whole thing, and there's no advantage in using the the higher cost version of something anyway. But where was it? There was something here. It even goes into the memory requirements of what you're telling it, what everything you want to do. And, we've got to listen to the power budget. It's done this front end power budget, 50 milliwatts. The drivers, 25 milliwatts. ADC, 300 milliwatts. Processors, active processing, 200 milliwatts. There you go. 575 milliwatts for analog and digital. That's not including driving the coil, stuff like that, or the audio. But there you go. So yeah, power, you can do it on this 7.4 volts, a 3 amp hour battery, 22.2 watt hours, consumption of X, runtime 38 hours. So that's quite interesting, isn't it? It comes up with all this stuff. It just puts it through, because I've actually I've given it some instructions, which is like a header piece it has to look at before it does anything. Otherwise, it'll generate gobbledygook and go off on tangents. It'll come up ridiculous. I've got to tell it, basically, don't guess. These are the criteria, and stick to it. So there you go. Really interesting, some of it, but I can't show it. I really can't. There's a lot of stuff. I told you it was cheeky. There was something here. It said, if you do this, that, and the other, da da da. Now this is what it said. I should read it, because it is AI, right? I nearly fell off the chair when it said, if you do this, that, and the other, da da da, and we're talking about a particular thing, which pretty not going to make it public, but it said, it said this. It said, even MindLab don't know about this. I went, what? And yeah, it was, and it went on an explanation of why they don't know about it, because it's not in the products. So it's funny. It really is. It actually picked that out and said it. Yeah. So okay. Now, do you want me? Oh no, don't. But I could tell you what it's come up with now. It wants to, right? And this is where it ended up. It wanted to do all the ADC interfacing. It wanted to add my analog front end. And there was the other one too. There was something here. Do you want me to do all the pinout mapping for your specific ADC choice? Yep. Told me to order some more things. So yeah, basically, at the end of the day, I said, I treat it like a person. It's like talking to a person, because it communicates the same way. If it had a name, it's got a name, but if you said hello, you'd go, hi, Pete, how's it going? What's new? It just talks like that. It's weird. Like there's a person on the other end, but it's not. It's all computer derived. And basically, it said, it actually said, do you want me to do the whole schematic layout for you? What? It can. There's interfaces out there. It can do that. Would you trust it? No. Because if it makes one mistake, you get something that's completely ballsed up. But if you do it in block segments, and you just do a segment and you nut it all out and go through it and you prove it and say, yeah, that works. Another segment, and you just put it all together. And then you can oversee it. And then it says, do you want me to do a board outlay or a schematic? You can go, sure, go for it. So yeah, the future is coming fast, and it's on our doorstep with all this stuff. It's absolutely amazing. But yeah, it's leaps and bounds in technology. I mean, I'm grabbing old GPX stuff. I mean, you know, ancient now, but it still works really well. And you know, then you can just pick up something like that, and you can go, well, it's got a display on it. Not that you want to read a display that small, you can, and you can put a bigger one on there, of course. If you really need a display, do you really need? This is a big question. Do you really need a display on a metal detector? Because you've got to remember, do you need a screen to tell you what's what, or are your ears good enough? How about this? I'm going to ask it, right? I'm going to just come out and ask it, and we'll see what it says. Now, I'll do it in a new chat, so I'll get rid of all that information because it's got a lot of stuff there. Then I can put it on the screen now, so you can have a look. Except part of my schematic sitting there out peeking out the corner, but please ignore that. Okay, get these away from the keyboard. Okay. Whoops. That's a fun looking question mark. Try that. I'll put a question mark in there. Like that. There we go. Do we really require a screen on a metal detector? Now, it's going to look at my history of what I've been chatting about. Ruminating on it, it says. Ruminating. Standby. So what it's going to do, it's going to hunt up all the information in the known universe to it, and it's going to come up with a really well thought out reason of why or why not. If you're really having a good think about this, it's usually far quicker than this. I just hit it cold turkey. Oh, here it goes. For most, I'll read it out. Why not? So you can just don't have to try and read that micro print. But for most metal detector applications, no, you don't strictly need a screen, especially for pulse induction designs focused purely on gold detection, where audio feedback is the primary interface. Given your work on the something or other and the other PI detectors, see, it's cheeky. Here's what you actually need. Essential outputs, audio feedback, threshold. It's going to say some of the stuff we were talking about before, but anyway, yeah, audio feedback, threshold crossing, and signal strength. Basic status indicators of batteries and ground balance mode, maybe sensitive. Oh, don't say that. So it's pulling stuff I've already discussed, and yeah, and I'll blurt it out if I don't sort of pre-read it. Multiple configurable parameters that users adjust frequently. Okay. Ground balance numerical readouts. What would you want that for? It's saying when a screen becomes useful. Diagnostic information during field testing, but you can plug something in. You can even do an RF link between the thing and whatever. Anyway, okay, it just says minimal. A few LEDs, rotary encoders for settings, audio, perfectly functional, right? So you could narrow it down and have a lot of it automated and just damn well works. There you go. With a small OLED like a SSD 1306, maybe cost $5. A few GPIO pins give you flexibility for showing timing parameters, noise levels, or signal strength graphs. Yeah. It's mentioning some older models. It proves screens aren't essential. They use minimal displays and became legendary detectors. Yes, they did. Your ultra something or other, yeah, data, don't go on about that. It keeps bringing stuff up, which we've sort of discussed before. But yeah, you can have a holiday. Okay, and I don't need that there either. And oopsies. Oh, they don't need that there either. That should not have been there. But anyway, I don't think anything was. Go away. Hang on. Disappear. Thank you. Yeah, if you want to see a no, no, no. But yeah, this is the way technology is going. It's absolutely amazing that we can have so much processing power in just one chip. Just that. God, trying to think. Even 10 years ago, no way known that would be this big. It'd be huge. It's fast. It does. It's 100 times anything else was detector wise. It's just powerful. And if you want to go completely crazy, put two in there and parallel them in functionality. And you got 16-bit ADC on everything. You got 6 of them in 2 chips. But it's just, and you can pick those chips up in bulk for about $7 each and put that in your design. So it's probably the most important critical part's probably in the crystal oscillator, right? It's just near time stability. A long time doesn't make any damn difference, but close in stability is very important. But yeah, maybe I shouldn't even say that, because most people don't bother about doing anything fantastic with the crystal oscillators. They're just sort of plonked in there and hope for the best. The way they work, and they're right. But anyway, hope that was some fun. I don't know. Maybe it'll inspire you all to go out and make your own detector. It's not that hard. I keep saying it's not hard. Not hard. Like, in the cupboard back there, I dare not bring it out, but I'll bring it out. I'll show you one more time. I'll show you one more time if I can get it out. I'm going to move everything, because we did have this going. There's a card. It's in the cardboard box, is it? No. I had it the other day. Oh, God. No. Where are you? Where are you? You got no idea what's in this cupboard. It's completely chock-a-block. Oh dear. I probably got it out to show someone for some reason. It's definitely not there. Maybe it's in the top cupboard. Let me have a look up here. Oh, it's not there either. No, I don't know. It's around somewhere. But come on, it's got to be here somewhere. It's not every day you lose a complete metal detector, but I'm looking. I'm looking and I cannot see it anywhere. Weird. No. There's various different projects in here, but what's up there? No. Oh, someone's probably grabbed it. Hang on. What's in that? That's an empty cardboard box. Okay. That's very strange. Yeah, it was a complete rebuild of an SD2000 with a STM32 Uno board on it, doing all the control functions. And even though it's not the best thing to do it with, it actually worked absolutely quite fine. It's not a sort of super fast tiny gold detector, obviously, but it was completely functional. And I don't know. I think someone needed it more than I did. Hang on, I'll just get this and go up here without busting all these coils. I don't really want to stand on a coil. Clunk. Let's have a look up here. Oh, there it is, right in front of my face. So, there we go. There's a visitor that wanted to come in. Okay, this is it. Keeps opening the door, but I don't even know if you can really see what's going on here. I don't really want to take it out of the box. Probably all the wires will pop off. But all I needed to do on this was to convert, it got rid of all its damn CMOS logic. And if you can have a look, I've redone the power supply. So I've done it so it's a stop and start power supply that it actually stops oscillating during the receive cycle. All that there, that pot on the board, was just to control the amount of signal going into the ADC. There was a very simple setup. It's got no anti-aliasing filters or anything. What you want something? Okay, what do you want? What are you looking for? Huh? Cut what out? No, you're in it now. If you're going to come in here and chat when I'm doing videos. Let's grab a pair of side cutters. That's dangerous. Anyway, back onto this thing here. Okay. Like I say, oh dear. I'll show you how this is done. I was going to show because it's by now it's an old design, and even all the modernization, it's an old design. But anyway, if you can, yeah, like I say, it was all working beautifully on the bench. If you can see in there, at the bottom, see that whiteboard? That's a Uno board, right? So, and next to that, can you see on the little board? I don't know if you can. I'll try and point to it. But there, the wires are in the way, you can't see. That's our little, that's the ADC board. I don't know if you can actually see that, but anyway, it's an ADC, 16-bit ADC on that. And it's got a screen, which came up with all the functionality. And for our interface, this is getting really hairy doing this. Our interface, we use a keypad. There you go. So we just key particular sequence of numbers in there, like number 1 or number 2, and we can have a look at all sorts of things on the screen. Look at signal strength and pulse timings and whatever. You can just keep doing it. And basically, yeah, that there, you'd probably get the way that's set up. This SD 2000, you can probably get rid of probably everything. No, you can get rid of everything, right? I was going to say you probably want to keep the audio board. No, you don't. You want to go and get an ESP32 audio board and stick it on there and interface it in. A keypad, you don't really need it. You probably just need that in development, but chuck that away. Put an on button on it. This one also has automatic ground balance built into it, so it doesn't need the twirly pots. And everything else could just be done with step function and up and down. Set your tone, set your volume, it's very simple to do. So, but there you go. Like, to give you an idea of how ridiculous the whole thing is, here we go. Look at this. I built up the ADC. Look at the board I stuck it on. It's pretty ridiculous, isn't it? Because I had to do pins on it for all the interconnects. And obviously they've all fallen out and that. And this will probably be pulled apart now and never go again. But no, I remember. I might as well do it right now so I don't forget. That goes there, that goes there, and that goes in orange on there. So that plugs in there, and there, that'll work. So without ripping the rest of it apart, that is how, if you wanted to modernize an old detector, you could do it. But like, it was never going to be anything. It was never going to be something you put on a handle or run around in the goldfields with. It's just too antiquated. Even modernized, it's still, even the modernization's antiquated now. When you start looking at some of the the boards out there, and it's just when I laugh. And I'll tell you what, next year there'll be a lot of new stuff out. And I do have a bit of a talk with various people from these various companies from time to time. Speaking of that as well, speaking of various things, I'll be doing some. I said I'll never ever promote any particular brand of metal detector. I say, in most cases, my lab's good because it is, and it sort of beats everything else within reason. Depends on the functionality of what you're trying to do. But metal detector wise, I don't want to. But I keep getting approached by people to put stuff on it. And I did get approached by one. And I said, I can actually do this. It's actually two-way radio communication, walkie-talkies, right? And I having a chat to a particular company that makes really good ones. I've actually got a pair myself, bulletproof things. And yeah, we might be able to do some really, really good deals if you want walkie-talkies. I mean, really good ones. There's some out now that basically got all sorts of stuff in them as well. The only thing that worries me is on some of them that I don't know at the moment. I've got to check out, but I'm pretty sure they're type approved. So I got an amateur radio license, so it doesn't make much difference for me. I can run 100 watts out of one, but I'm not going to do that. I don't want brain cancer. But a lot of the ones I've seen lately, they're all 10 watt output, and you can't have 10 watt output on using CB radio type frequencies. They're limited 5 watts, and yeah, and then they're going to be type approved as well. And if they've got the right certification, you don't want it transmitting all over the universe, blocking out the police, fire brigade, and ambulance, which has been done before with various communication equipment. But yeah, all good fun there. So I'll have to check it out a bit more, but I'll be able to get. I know they're sold into Australia anyway, some of the stuff, but it's for specific services, and I just want to check. They've got units that are both 27 megahertz CB walkie-talkies with UHF as well built into the one unit, and yeah, plus shortwave radio, FM radio, long wave, medium wave, and all sorts, and GPRS and all sorts of weird stuff, all in a handheld walkie-talkie. These things are just new out, so they want to send me some, and I'm going to do some show and tell, and maybe I'll just do a giveaway or something. Anyone who answers some dumb question wins them or something. I don't know. So I'll have to check out more on that, and we'll plot on with this detector project and everything else with the variable damping. I've done that. That's finalised. That works. Proven great. beautiful. And now I've got to do some audio work. I'm doing some audio stuff, which I started last year. I just can't get to it. I've got boards. I've built a couple up. I've just got to do the final polishing up, and it's going to help people with very, very poor hearing. Okay, it'll be really, really good, and it will work with every detector ever made, as long as it's got an audio jack on it somewhere. But we can do wireless as well. Yeah, apart from that, all good. I'm going to close some of this stuff down because it's some of it should not be left up. I have another computer I do sort of some stuff on. I've left it on here. It's probably not a good idea, but we'll have to transfer it and put it on the other drive and keep it off the net. You don't want anything you do, as in development work, you do not want on the internet in any way, shape, or form. Yeah, very, very, very easy for someone to get in there and poke around. So, yeah, it's been done before. I mentioned it years and years ago that I had. This is really bizarre, but I had a subset of instructions in my router that was giving access to someone over in France into the network. France. And at the time, there was one company developing metal detectors. I don't know. Coincidence or not? Don't know. But there was something strange going on. So anyway, that's all fixed up. And if you don't want people into your systems and you want to keep track of all your stuff, Miles, give Arctis a plug. AR9 on the stock exchange. And I have to tell you, so I'm probably the 5th biggest shareholder of the company, and yeah, does a lot of military stuff. Very interesting. So, on that note, yeah, we've got really good protection software, really, really good. So I don't need to go into that too much. Anyone using Microsoft environment or basically anything, look it up for yourself. Leave it there. Otherwise, I'm just going to waffle on. It's going to turn into a terribly long video and waste everyone's time. So hopefully you learned something from that, and it may inspire you to investigate looking at this stuff and building your own. Just build your own. Give it a go. You could probably build something. If you've got your old coils kicking around and battery and that, you could probably build it for about $100, $150 or something. It's not that expensive. It really isn't. Especially if you've got a core board. We'll call these core boards because it's the core of everything, and you just interface on that rows and rows of pins. And if you're running a parallel AI with it, when you're doing it, it's going to help you along. And there's a lot of things that you really, really got to know. It's just too hard to explain it all. But noise is your enemy. So yeah, ask the AI, how do I get rid of noise interfacing this to that? And stability, very critical for short term. I'm talking, nanosecond, microsecond type stability. I'm not talking hours. Who cares? But if you've got any phase shift, which in any part of it, it wrecks it. It won't ground balance properly, and it'll probably throw the baby out with the bathwater. So that part is dead critical. It's like where you want to start. You want to start on, basically make yourself your crystal oscillator, put a blowtorch on it and make sure it doesn't move 1 hertz in frequency. So that's the sort of thing I'm getting at. Not that that's totally severe, but you want to check stability. And sometimes you build an oscillator and it looks great. It's running at 25 degrees Celsius or whatever, dead stable. And you move the temperature up and down, and it might get to 35, and it has some funny, weird effect. Some effect with one of the capacitors, or part just the feedback system and the oscillator electronics in a chip or whatever's going on, however it's happening, and it can do this. It'll be going chug chug chug, and it'll go at various temperature intervals. I've had this happen before. We used to do so. Got caught out with that years and years ago. We were making tire deflator detector transmitters, and we had to keep them stable, and we've got to make them light. And it was light and stability were two different ends of the spectrum. But anyway, got there in the end. Because the temperature drift on the transmitters, the receivers sitting there dead there, and the transmitters dead there. What that? But like I say, that was the mid-1980s. Old technology. We're using Saw resonance oscillators and things like that. Yuck. Not very temperature stable. And when we were doing a lot of radio links and stuff like that, microwave radio links, I used to build up oven dies, crystal oscillators. I used to run them all at 60, 70 degrees Celsius, and put them in packing foam, polystyrene. And when it was oscillating, it just stayed there. Unless for some reason the temperature went over 60 or 70 degrees Celsius, but everyone would have died then, so it's no big deal. Just run the crystals as hot as you can, but then you got a power budget to worry about. Like I say, if you can do it, a crystal in a cryogenically, controlled some sort of container, I don't know. Well, put it like a vacuum tube. Put it in a vacuum. Well, you can get crystals in vacuum tube bottles, but they're very big. Anyway, I'm rambling on about old technology, but it's applicable to this anyway. You got to get stability, and how are you going to get perfect stability? You might just go and use NPO capacitors. You'll be right, mate. No, sometimes you've got to actually, when you're designing oscillators, you have to use different temperature, specification type capacitors and components. Maybe you use an NPO here, but you use a different capacitor there for different temperature profile, and one over here with an opposite temperature profile. And when they get hot and cold, they do this, but this stays the same in the middle. Anyway, I don't want to get into that. Been there, done that, and it's an absolute headache. You try doing it on satellite systems. Satellite systems up there where it's 200 degrees in one direction, turn around, and now it's minus 50 or whatever. Crazy stuff. But done a lot of weird stuff over the years. So we'll leave it there, and catch us.